Hello everyone. Just wait for some time for the rest to join and then we'll start. Hi, can you hear me?
Hello. Yeah, I can hear you.
Okay. Can you see my screen now?
Yes, I can see it.
Okay, okay, great. So what we are going to look at is a different machine learning algorithm that is related to, or that is otherwise known as the support vector machines. Now, I would like to understand the concept of support vector machine in a different way. So what I'm going to do, I'm just going to create a lot of cells, right? And then I'm going to explain the concepts first, post which I'm going to go to the code. If we have time, but else we can start by lecture tomorrow also. But for the coding part, I've taken a data related to wine quality. So I'll just quickly show you the data. There's no specific reason why we have taken this data specifically for this example. Right? Actually, we could have taken something very, very complicated, but I'll try to find if something is there which is really complicated, which I could find. Let's say it may be there in the data sets which sklearn already provides. sklearn has a library or a module known as sklearn.datasets where a lot of data is already available. So most probably we can try and find something really complicated like let's say letters or the kind of a machine learning problem where we are trying to let's say identify uh, uh, the handwritten letters or words, right? So something of that level, something of that complexity is really the ideal choice to use it. You will understand why this is going to be the case. Let's try and understand how this really works. Okay. So to understand this, there are two ways to do this. Um, uh, uh, just a moment. Uh, just a moment, Ravin, yeah? Just a moment. I'll just reply to one person and then I'll come. Yeah. Okay. So there is a geometric way to understand how support vector machines work. But before we go in there, let's try and understand it from a different kind of perspective. What I'm going to do is that I'm going to draw a person who is, let's say, standing over here. Right. So I have a person who is standing here, and what I would like this person to do, right, is that he has a line of sight which is somewhere in this direction, right? So he's looking at this kind of a direction. So he's looking into a direction which is somewhere in this side, right? So I'm going to give him uh, some object, okay, and that person is going to look at that object and he's going to tell me how much percentage of the surface area, how much percentage of the surface area that person can see. Okay, so for example, let's say I give him a orange football. Okay, the football is really very big, so this is a football, and this person is now looking at the football. So approximately, you can say, let's say, can approximately say that this is the portion which this person can clearly see. This is the portion of the surface area which he can clearly see, right? Because this is the line of sight, right? So he is able to see it from this kind of a perspective, and hence he's able to cover only this much area. He's not able to see the back side, right? This is the back side of the ball. Back side he cannot see. Okay, front side is this side. Front side he can see, but not entirely. So he cannot see 50% of the surface area of the ball. He can only see some percentage. Let's say this percentage is equal to let's say 40. It's just a rough figure. Okay, this is let's say 40. It maybe can even change this. Let's say I'm just going to say this is equal to 46. Okay, this is equal to only 46%. So 46% of the surface area, this person is able to see from this place. Unmute. So now what I do, just to increase the complexity, what I'm going to do, in front of this football, I'm going to put a tennis ball. Okay, so this is a tennis ball which I've put in front of the football. So obviously, now the sight is blocked, right? So if this is the line of sight, obviously there is a projection of the smaller ball on the bigger ball, and hence this much portion, let's say, is no longer really visible. So this person, let's say, person P, okay, is not able to see or is no longer able to see 46% of the football by standing at this position. Let's say this position is P0, and he is not able to see the entirety of that ball from this place. Okay, he is not able to see the entirety of that ball from this place. But then he may be able to see, let's say, similar percentage of the surface area for the tennis ball. So I can say that now he is able to see 46% of the tennis ball, but he has lost at least 15% of the view, okay, for the football, right? So now the percentage of things that he can see being at position P0, let's say, is going to be football is 36 minus 15. So let's say he is able to see only 32%, right? Or only let's say 31%. And the tennis ball, he can see 46%, right? Tennis ball, he can see 46%. Now my question to you is, I'm going to, or I hope you understood the problem, right? So he is a person who is standing here, and I gave him a football. He was able to see 46% of the football. Now I placed a tennis ball in front of the football. So his view is blocked, right? So now he is not able to see, let's say, 15% of the surface area. That is blocked, right? So I am just approximating it. This is not the right way to calculate it. You can ignore the math now, but I'm just trying to do the approximation that now that he is not able to see that leftover 15%, so he is able to see the rest 31%. The 31% surface area of the football he can see. But 46% of the tennis ball he can see because tennis ball is really in his line of sight and he can look into it clearly. Right? Now, my question to you is if you are able to hear me still, if you have understood this kind of scenario, is that I am giving you three positions P1, P2, and P3. Out of these three positions, where would you like this person P? Where would you like this person P to move? He is free to move, but the balls are not free to move. Okay, you are not supposed to move the balls. The balls are going to be stagnant. They are going to be fixed. Okay, the balls will be fixed. The person can move. You can move the person to position P1 or to P2 or to P3. You move him to any position, but the only condition is the position which you choose should give him maximum view of both the balls. Right? So in this kind of a scenario, which position are you going to vote for?
I think except for P1, both P2 and P3 sounds equal.
Okay.
Both will
So
both will give an equal
P2
view.
you will have a view which is something like this, and from P3 you are going to have a view which is something like this, which you are saying is exactly equal, or let's say close to equal. So P2 and P3 are approximately, let's say, equal to each other, right? So out of these two positions, let's say we do some kind of a calculation and we decide that P3 is the best place, right? So let's say that we do some math and we find out the percentages at position P2. We do some math, we find out the percentages at P3. We finally come to a conclusion, okay, P3 is the best place because it has higher, let's say, percentage, okay, of both the balls, okay. So let's say we select P3. If I select P3, all I'm doing is that my objects are at the same place. Okay. just to get more better visibility of the observation. I'm changing this person's position or the perspective, right? So that is exactly what I'm doing. I was looking from this side, right? I was looking at it from this side. Now I've just changed my way of looking at it, right? I was looking at it, let's say, from the front side. Now I'm looking at it from the side view, right? So rather than having a front view, now I have a side view, right? Just a moment. Okay. I'm sorry, Bhai, there was something which I needed to write back. Okay. So in this case, what we understood is that for this person to have a better view of both the balls, all we did is we changed the position. We started from P0. We were initially at P0. We just changed it to P2 or to P3. We decided some of these two or one of these two are actually good, right? As per your initial thought, it was, except P2 and P3 both are same. Then we do some kind of maths, let's say, which you don't have to bother about right now, right? But now, basis this kind of a comparison, we found out that this percentage is higher, hence we selected P3. So what we have done over here is somehow, okay, doing some kind of a calculation, okay, we have changed the perspective, right? We changed the perspective so that we can see better view of the entire thing, right? This is exactly what SVM is going to do, or this is exactly what we are going to learn how SVM is going to do, right? How SVM does that is, let's say, you have a data which is very simple, okay, a very simple kind of a data. So you have two classes in the data. Okay, you have this one class and you have this other class. Okay, you have this other class of the data. You have two classes of the data. Now SVM, or you are using SVM to do the classification here. So let's say this is a very simple kind of problem. These two are the features, x1 and x2. Okay, x1 and x2 are the axis. I'm just doing a scatter plot and I'm able to find out using, let's say, color coding and legends that these are the two classes of the data which is there, right? Now what I am doing, okay, using SVM, or what SVM in this case is going to do, this is a 2D example, and this is a binary classification kind of an example. This is a very simple thing, and it is going to do the same thing as it used to do. Okay, it is going to do the same thing as it used to do, just like any other kind of a decision boundary, or just like any other kind of a classification algorithm which we have seen. So all it is going to do, it is going to create a decision boundary, something like this, right? Why is it going to create a decision boundary, something like this? Is because, okay, why is it going to create a decision boundary, something like this? Is because it's going to create a line which has good amount of margin around it. So let's say these lines that I've just drawn, which are the lighter colored lines, right, or not so bold lines, are the lines which are near to that line. Okay, so this is actually my decision boundary, which SVM comes up with. Okay, SVM only results in the decision boundary, which is going to bifurcate the two classes, right? So if you have a new point on this side, okay, on the top side of the boundary, obviously that will belong to class X. But if you have an object which is at the bottom side, obviously that is going to belong to class 0, right? So this is what, or this is how the decision boundary is going to give the prediction. So what about these two lines, these two smaller lines? These two smaller lines are creating an area over here, And this area is also known as the margin, right? This area is also known as the margin. Whatever area it has encapsulated is known as the margin. The basis what kind of SVM modeling you are doing, right? It can create two types of, let's say, margins. One is known as soft margin, and the other is known as a hard margin, right? Usually, SVM will prefer doing a hard margin, which means the size of the margin, right, or this distance here, right, it is going to be very high, right, or it is going to be as maximum as possible, as much as it can have, right? This is the reason why, in some cases or in some texts, you will also see that SVM is also known as the maximum margin classifier, right? It's also known as a maximum margin classifier. The reason is very simple. It is inclined, or it's a model which is biased. I should not be using that word actually. So we already know it has a different kind of a meaning when it comes to machine learning one, but you can say that it is more inclined towards creating a model or a decision model, which is a very big margin, right? But of course, it can adjust with the data. You can make it adjust with the data also, depending on how you are implementing it, right? And you can make it a soft margin kind of a classifier also, where the distance is not so high. I mean, I'm not saying it is going to be minimal, it is going to be zero, right? The margin is never going to be zero. Margin will obviously be having some kind of a value, but the value can be very small or the value can be very high, right? So if it is very high, it is a hard classifier or a maximum margin classifier, right? Else, if it is a soft kind of a margin, right? In other words, this distance is smaller, right, as compared to uh, a very big kind of a value, right? Then it is also known as a soft classifier. If this distance is small, is relatively small, right? So this is what SVM is going to simply do in case of a 2D case, in case of a binary classification problem. In the same way, it can handle multi-class classification problems also. So let's say if it had some other objects here, right? If it had some other objects here, it may have created a decision boundary somewhat like this, right? Now the points which are across the decision boundary, right? The points which are across the decision boundary, right? Let me just remove that other class which I just drew, for example. The points which are there across the decision boundary, these points, especially the ones which are closer to the margin, these are known as the support vectors. They are given this kind of a name because basis them only, this algorithm SVM is trying to understand how good or how bad this decision boundary or the margin was, right? How it is trying to do that is because within the margin, as you see, I have no points. So it has created a margin and a decision boundary in such a way that within that length, within that range, there is nothing which is allowed, right? So this is the way in which it is clearly classifying the object. So it is creating a very hard kind of a rule kind of a thing, right? And it is obstructing anything wrong going on, right? So if you give it a data, it's going to try really, really hard to create a hard margin or a maximum margin kind of a classification, where the margin is going to be very high, so that when we are doing the predictions, we can be very, very sure that whatever we are predicting is really good. This is one of the reasons why usually you will see that more complex the data, or I will also explain why it works in case of more of the complexity. But in case of HVM, the accuracy percentage, for example, if you have a balanced kind of a data, then accuracy percentage, right, is usually very, very high. As compared to any other model, it's usually higher. Okay, just like we saw that in case of, let's say, random forest, it is going to be higher than the decision trees. So in the same way, in case of HVMs, it is going to be higher than any other generic classification algorithm, right? It's going to be higher than any other generic classification algorithm. Okay? Now, this was a very simple kind of an example. We'll come back to this kind of a simple binary or multi-class classification problems where we could easily draw a boundary line at a later stage, because I have to explain you to a specific kind of parameters, okay, which comes into play when it comes to SVM. But that is at a later stage. Let's try to understand where the real power of SVM lies. This is not the real power of the SVM. If you look at this classification which it has done, obviously you could have also fit a sigma to do this kind of thing, right? If you look at it carefully, okay, if I just take another kind of a color, you can clearly see a sigmoid curve also fits over here. If I try to do a sigmoid curve, it is also going to fit over here. If I'm able to represent the zeros and ones in a logarithmic scale or in some kind of a scale, which can actually help me use a logistic regression kind of a problem here. It may not be as good as it may be because of this kind of hard boundary which it is trying to do. Also, logistic regression being uh, 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 a model which is using sigmoid function, which is using the returns or results into two values 0 and 1, it may not be very good in case of multi-class classification problem, but that is not the real power of SVM. SVM is doing quite good in this case because it's creating a decision boundary with a margin this time. Either the margin can be soft or it can be hard, but it's not allowing any objects within the margin. In that sense, it is doing quite well, but that does not mean that naive Bayes or KNN or logistic regression may not work here as well, because this is a very simple kind of a data. It's a 2D representable data. It has only two features, right? I can represent it into a 2D graph like this, and it is a binary classification kind of a problem. It will work. Now let's see a different problem. Okay, let's try to see a different problem. Here, what we are going to look at is a problem where, let's say, you have two data sets. And the data sets look like this. You have two classes of the data, you have two features, x1 and x2. Again, for the simplicity, I'm just drawing a 2D kind of an example with a binary classification problem. Okay. I have two data points, or I have two data classes, which are now looking like this. That cross was one class, and these circles were one more class. Now you cannot draw a decision boundary so easily in this case, because wherever you fit that line, right? Let's say you want to fit the line over here. At any point in time, the line is going to be always wrong because 50% of the classifications are always wrong, right? You cannot fit a straight line, right? In this case, what can you do? Right? In this case, the question is, what can SVM do? What SVM is going to do is similar to what you did with that person. That person was standing at P0. You change the perspective, you change the position to P2. And that is exactly what SVM is going to do. Okay, by default, it is going to use a technique to do it. You can even override it. What it is exactly going to do, let's look at it. You imagine these are objects which are falling on the ground, and you are looking at them from the top view. Okay? You can try to imagine these are objects which are falling on the ground, and you are looking at them from the top view. Now I am asking you to do some kind of a mathematical magic, and I would like you to change your perspective. And the way you have changed your perspective, or the way you have done the mathematics, is that now you have created the third axis, which is, let's say, x1 square plus x2 square. This becomes your third axis z. Now you are converting 2D into 3 dimensions. The third dimension that you have created is, let's say, x1 square plus x2 square. This axis x is still x1, axis y is still x2. Now you have added a new axis z, which is x1 square plus x2 square. Now how the points are going to be distributed, the points will now have a higher dimension. The points will be looking something like this. The crosses have gone to a higher point, and the circles are here at a lower point, which means I can actually put them through a cubical kind of shape, or a very, very difficult or a different kind of a shape now. So the data has taken a shape after I have done this activity. After I have increased the dimensions from 2 dimensions to 3, I have created a new axis Z, right? This is by simple means of, let's say, feature engineering. I created a new feature, let's say, x1 square plus x2 square. You can try to understand this, like you are creating a new feature. You have two features, x1 and x2, already in the data, right? That makes your data two-dimensional. Now you're creating the third dimension using x1 and x2. Okay, by this formula, let's say this is the formula, right? So you now have a new structure of the data. Now what you can do, you can create a decision boundary very, very easily, right? You can create a decision boundary which is going to be very, very easy. Okay, and the way you can create it, I don't know why this is not really coming up. Let me just undo this. Okay, let me just go ahead with this. We can come up with a decision boundary which is something like this. Now you have three dimensions, right? So in three dimensions, a line can be represented as a plane. So now you have a plane where you have represented the data, right? Anything above this plane is going to be part of X class. Anything below this plane is going to be part of the zero class. And now you have a decision boundary with a margin, right? As good as this calculation is, the margin is going to be high or less, right? You can still be able to control the margin, how much good or how much small or how much big the margin is going to be. This is the kind of calculus you are doing, right? So this is the crux of SVM. This technique that we have done, okay, the technique that we have used is also known as kernel trick. Okay, this is known as kernel trick. There are many tricks which we can do. As a matter of fact, the first diagram which we draw, which was a linear kind of a line, right? That is also known as a kernel trick. Okay, a kernel trick can be linear. Okay, it can be polynomial, right? It can be radial based function, and it can be sigmoid. Right now, linear, polynomial, and sigmoid are very easy to understand. You can just try to imagine that linear is so easy, we don't have to explain you also, right? Because linear is what we just saw in the last example, right? The line which we draw was a linear line. In case of polynomial, I'm just going to change my features from x1 to x1 square or x1 cube and so on. Radial based features are going to be very, very difficult to understand. They are the most complicated ones actually because they can take any shapes. I can show you some examples where radial based functions are used. But sigmoid is also easy. You know how the segment function is really calculated. Right? We looked into it when we looked into the logarithm or the exponentiation that we use, right, in case of the logistic regression. So sigmoid is one way. Sigmoid is one function by means of which we can do this kind of feature engineering, which SVM is going to do by itself. You don't have to do it. Okay, SVM is going to do it by itself. You can specify the parameters whenever we are tuning the model, right? We are going to specify the parameters. In that way, we are going to tune the model. And based on the parameter that we are going to produce, it is going to create the model for us. But by default, it is going to use a radial based function. So it is quite important to know that because scikit-learn, okay, scikit-learn by default uses RBF. We need to know what really RBF is. RBF is useful in cases, let me just remove the run for 1 minute. So RBF is useful in cases where we have scenarios like we have some data which can be classified like this. Okay, so we have one type of data which is classified like this, right? And one type of data which is classified like this and like this. So for example, this is one class of the data which is given by these pink process here, right? So which are given by these pinks, right? And this is that other kind of the data which is given by the blue circles. Okay, so when we have such complicated shapes or such kind of complicated distribution of the data, SVM is really going to work with it, right? In that case, we can make use of SVMs. We can create this kind of, let's say, distributions. Again, we are talking about creating the decision boundaries, or we are looking at them from a top view. If we look at it from a different kind of horizon or in different kind of dimensions, although we as human beings cannot see beyond 3 dimensions, right? Or we cannot really visualize anything beyond the 3 dimensions. But if we try to convert this diagram into some kind of a different way to look into it, then most probably it may also look like something. So let's say this is a three-dimensional kind of a setup. So here is a one row of the data which represents this data, right? And then we will have, let's say, we are going to have some data points here, and we are going to have some kind of data points here. No, I'm sorry, I did it wrong. So these data points will not be in the same scale as they are. So let's say some of the data points are here and some of the data points are here, right? So here it has created the areas. It has been able to clearly segregate the areas that belongs to each and every of the data, and most probably now the decision boundary, okay, let's say, is going to fall over here. Right, so this is the way it is going to differentiate between one class and the other class. Right, this is the main aspect of using SVM. But this does not make SVM really very good. it actually has a problem attached with it. The problem is very clearly, as you can understand, this is the kind of calculations which you are asking, right? Which you are asking to do, right? Or which you are expecting the algorithm to do. If you increase the complexity, the mathematical computations is going to increase. If you give it something very, let's say, a very kind of a large kind of a data, right? It has to do the conversions. Then it has to do this kind of, it's a feature engineering which we did. We had only two columns first, X and Y. Now we created a third column Z in a higher kind of dimension. All these kind of computations will be applicable on that entire large data, because SVM is an eager learner. It is an eager learner. It is going to learn these kind of patterns during the training stage itself. Because in the training stage itself, it has to come up with this decision boundary. This boundary has to be created while it is learning from the data. It can't wait for a new or unknown or a query point to come to it, and then it is going to become. That is not what it is going to do, right? Clear it is that it has to create the decision boundary first of all, and then I can make the predictions out of the decision boundary using the model, right? So if you have a very large kind of a data, if you have highly dimensional kind of a data, then SVM will work very poorly when you are going to look at it from a time and space kind of a complexity kind of thing, right? So that's, or those are the places where SVM may not really work well. That is where we have to do a lot of scaling of the data, or we may need to do very good feature engineering or feature selection from the data and so on, so that we can limit the dimensions to a very good extent and so on. So later on, we are going to, when we learn about unsupervised learning after this, because supervised learning is almost at the end. Now we are going to look into unsupervised learning areas after this. So once we look into unsupervised learning cases, we will look into techniques like principal component analysis or LDA or TSNE, where we can do or we can take care of these kind of large dimensional kind of a data, and we can convert them into smaller dimensions, right? Without losing much information from the data. As of now, it will be very difficult for you to relate what I'm really talking about, but when we look into it, you will get the point, right? And then we can use that. Further, we can use that kind of a prepared kind of a data, and then we can use that to fit a model using SVM, which may well be very good in terms of time and space kind of a complexity, irrespective of how or what kind of, let's say, computational system you have. Right? So, irrespective of what kind of computational system you have in place, it is going to work. Right? But SVM will not work out of the box like so easily or so computationally friendly as if it was the naive Bayes algorithm. Right? Because naive Bayes, the calculations are very simple. It was really into the probability world, and all it was doing is, let's say, summations or let's say multiplications and doing the division. In that case, it was very easy. In this case, it is not going to be easy because it depends on the kernel that it is trying to calculate, right? And hence, it is going to be very calculated, right? It is going to be very calculated in terms of the training data. It is going to take a lot of time, right? But obviously, it can handle a lot of complexity in the data. That is the crux of this algorithm. It can handle a lot of complexity within the data. Whenever we have data that we cannot directly or clearly distinguish, this is what we do. Right? SVMs is a good choice when we are not able to clearly differentiate between two classes of the data. Because if we can, then I know I have algorithms like, let's say, distant trees, or I have algorithms like the earlier ones that I have already learned, which I can use very easily, and I will be able to do the prediction. Right? I hope it is clear until this point in time, Rohi. If you can just quickly confirm, or
Yeah,
if you
yes.
can, yeah. Okay. Let me go ahead and let me show you one example or two cases which I wanted to show you. Right. There are two cases which I may not even have to draw. I can show you directly on the blog, right? I can show that to you in the blog. So let me just search for that blog here. I'm not sure if this is the blog that I'm really looking for, but let's see. There are some good pictures which are there, which will help me to explain the scenario to you. I believe I have got it. Okay. I believe I have got it now. So this diagram is really good, which I'm going to use to explain things to you. right? So I'm just going to open this image in new tab, and I'm going to open this image into new tab, but they have not provided the explanation for another variable which I wanted to take. So I'm just going to explain that to myself, and then we are going to look into the other one, right? So what the first hyperparameter that we need to be aware of is called C. Okay, at least I don't know what is the full form of C in this context. I don't know what is C really referring to, right? But all I know is that C is a continuous variable. Okay, C is a continuous variable, which means it can have value like 0.01, or it can even have values like 100, right? It can have any values like this, which is natural number. The basis, the value of C, something strange is going to happen in case of the modeling. When we are doing the modeling, after let's say we have created a model M1, let's say we have total number of points in my training data, which is equal to 100. I'm trying to check how good and how bad it is, right? I'm trying to check how good or how bad it is, or maybe n number of points are there in the testing data. Okay, so I've already trained my model using 100,000 points. And then I have 100 points, which are my testing data. Using the training data, the model is trained already using SVM. Okay, I've used SVM to train my model. Now I'm trying to predict for these 100 points. I'm trying to check, or these 1,000 points, where I'm trying to check how good or how bad the model is. Okay, let's say there are two scenarios. Okay, scenario one, okay, is where I have 960 points correctly identified out of 1,000. Right? I have another kind of a scenario where I have 995 points correctly identified out of 1,000. This number sometimes even comes to 1,000 also. Sometimes we see that 1,000 out of 1,000 use cases are correctly identified. So scenario one is where I have an accuracy of how much? Let's say it is a balanced data. Let's say it's a multi-class kind of a problem, and it is a balanced data. Okay, just for the sake of it's a simplicity, I'll say it is a balanced kind of a data so that I can clearly say the accuracy is 96%, right? And in this case, the model's accuracy is how much? 99.5%, right? I have 99.5% accuracy in case of scenario two. What the C value is going to do is it is going to control, okay? It is going to control in which scenario I would like to be. So this is a very weird kind of a question, right? Obviously, I would like to be in the scenario too. I would always like to be as good as really possible. But is that really necessary? It's a question which we have to ask to ourselves. For example, if I'm looking into the probability of a person having cancer or the probability of a person not having cancer, then it is really important for me to have a very high accuracy out of my model, or the predictability of my model should be really, really very high, right? It should be very high, right? But when I am looking at cases like, let's say, whether a customer is going to churn or not, in that case, do I really need 99% kind of an accuracy? I really don't think so, right? But if we are trying to create a model, let's say this M1 model is for healthcare domain, or in case, let's say, this is going to be used by the justice department, where it is going to decide whether a person is innocent or not, then that higher level of accuracy will really be useful, right? That higher level of accuracy will be required in some use cases. It will not be required in all the use cases. In some use cases, it will be required. In some use cases, having an accuracy of 78% will also do, right? In our official working environment also, if I get a model which is 78, my manager may even throw me a party, right? So what I mean by that is 78% is quite handsome for many business scenarios which we have. If I'm able to achieve 78 to 80% kind of thing, it is more than, I don't really need to look into 99%, right? Keeping this in mind, how do I control this? Using this value C, I can do that. How? If the value of C is towards certain range, it allows misclassification. Okay, here I have 40 misclassifications. Here I have only 5. In the scenario 1, I have 40 misclassifications. In scenario 2, I have only 5. How much misclassification the SVM is going to allow? Or in other words, how much this model is going to be penalized? what is going to be the penalty of the model? Right? Internally under the hood, when SVM works, it gives a lot of, it's a penalty to the model if the model is not going to perform well. Right? How does that work in this case? In this case, it works like this, as it is explained over here. If C is small, the penalty of misclassified points is low. So a decision boundary with a large margin is chosen at the expense of greater number of misclassifications. So in this case, what is happening is the margin will be higher. It may even allow points to be within the margin. Right? It is going to create a maximum margin kind of a classifier where it is going to allow the misclassifications, which means it is my scenario number 1. Right? 960 out of 1000. I'm okay with that even if it was 860 out of 1000. Right? But if I have a C value which is large, SVM will try to minimize the number of misclassified examples due to high NLT, right? Which results in a decision boundary with a smaller margin, right? Right? So, in case C is high, the decision boundary will have a compact margin around it so that more and more classes can be correctly identified. In other words, misclassifications can be reduced. In other words, the accuracy of my model can be improved. Right? The accuracy of my model is going to improve. Right? That is the main intention. Right? This is what C parameter does. I have one more which is known as gamma. And to look into it, I'm going to look into these two examples. This is a multi-class kind of a classification problem where you can clearly see, okay, I have 3 classes. This is class 1, this is class 2, and this is class 3. Obviously, there are cases of misclassifications over here. Okay, I can clearly see there is a misclassification here. This point is too close to the decision boundary 1. So let's say this is decision boundary 1 and this is decision boundary 2. Obviously, we have 3 classes. To differentiate, I need 2 lines. That created the lines, and maybe there is also chances of the misclassification. So misclassifications is okay. Okay, if misclassifications is okay, I'm going to use a low value of gamma. Right, misclassifications is okay if I'm going to use a low value of gamma. But let's not look into it from misclassification kind of a perspective. What gamma really means is the understandability of the model. If you have a linear model, it's usually very understandable because now you can assign a coefficient to the features, right? If we have a linear model like this, where V1 and V2 are linear, separable lines, so these are straight lines. In this case, it becomes very easy for you to interpret the model, right? What happens if you are ready to sacrifice this simplicity, right? Because this model is really simple, you are ready to sacrifice the simplicity, okay? And you want to do something which you can see in this diagram. If you can see in this diagram, what we are doing, we are trying to do a lot of calculations within the model so that my decision boundary is so good that I don't want to make much mistakes. In other words, at the expense of not making more mistakes, at the expense of being more and more good, okay, in terms of the classification, what I'm eventually ending up doing is that I'm doing a model or I'm creating a model which is really, really, really complex. Right? This is a model which will be very difficult for you to have it explained to a manager. Right? The earlier one, right? The linear one was very easy for you to explain. This was really easy to explain. This was clear to our eyes also. This was very good looking also. Right? So we were able to understand this quite clearly. We were able to understand it quite easily. Right? But if we look at this model over here, this is really complicated. It's really, really complicated. Right? It is very much complex kind of. Right? Now, which model do you want is again, that is going to be dependent on what kind of, let's say, use case you are having, right? Also, the value of gamma is sometimes also related to the fact that how much underfitting or overfitting you have over the model, right? Because if you look at this kind of a diagrammatic representation, clearly, this looks like an overfit kind of a situation because the model is trying very hard to, in this case, create 3 decision areas, right? Create 3 decision areas A1, A2, and A3, which are really marking down the boundaries really very well. And obviously, this can lead to overfitting of the model, right? So we have to select a value of gamma which does not really need to be so accurate, right? That is no longer simple and it is going to result into the overfitting kind of a problem, right? It can lead into higher accuracy, but it can lead into overfitting kind of a problem. Instead, we can try to look into, if our use case is really going to support that, we can look into a model like this, right? Where my class was clearly differentiated into three areas using the decision boundaries B1 and B2. And my model is really simple to understand. I can clearly define the boundaries where the data sets are going to lie or where the new unknown point is going to fall on and so on, right? So linear model is where it will be easier for us to explain, because obviously in case of low gamma, if I'm able to create linear models with linear decision boundaries, obviously these are straight lines. The straight line, obviously, you know, it is going to have a formula mx plus c, right? So if you're going to have a formula which is mx plus c, if I just ignore the value of c for some time, I can still get the value of m, right? Which is my coefficient for the feature x. Hence, I will be able to understand which feature is really important, which feature is not important, right? So that kind of a thing is going to work. But in this case, okay, in this case, it is really going to be difficult because this is a non-linear case. Okay, this is a non-linear kind of a case. Right? In case of a non-linear kind of a case, I don't have the coefficients. Right? I don't have the coefficients. I cannot have the coefficients in this case because this is not a straight line. I cannot write an equation for this which is equal to y is equal to x plus. Hence, I'll never be able to understand what is the value of n. Hence, I may not be able to do feature importances automatically using the coefficients. I'll not be able to use things like RFE. RFE cannot be used. Right? If I'm creating a model which is so complex, RFE cannot be used because I cannot have an equation like this. Right? So this is the meaning of those two variables which I just wanted to tell you about. It is known as C and gamma. I'm also going to pass on this link over to you so that you can have a look into it. You could also look into the documentation which we have um, uh, in the sklearn itself. That is going to give a very good idea about what um, kind of the way in which sklearn has tried to implement it. Unfortunately, we wouldn't have time now, so let's take a pause here. We are going to close the session. We'll start back again from, let's say, next week into Monday, because tomorrow I will be traveling. So let's start it from Monday once again, where we are going to look into the use cases, right? So we are going to use that wine quality or wine quality data set related to red wines, and then we are going to try to fit an Azure model. In the meanwhile, let me also see if you have any questions, please do let me know, or else I'm going to find some kind of a data set which is really difficult, and then we can try to use it instead in that result. Right? Do we have any questions at this point in time?
No questions as of now.
Okay, then let's close the session. Yeah, let's meet again in the next week. Okay, thank you so much for joining. Thank you.
Okay. Thanks, Momik. Good night.
Thank you.